This video is your climate foundation, the kind that stops geography from feeling like a collection of random chapters. We'll move in a clear chain. First, the atmosphere and its layers, then why temperature changes from place to place, then the global wind pressure engine, and finally, how that engine produces rainfall systems, monsoons, cyclones, and fair weather. If you understand this properly once, you won't need to memorize climate again. You'll be able to explain it. Start with the atmosphere's structure in two ways: composition and temperature. By composition, the lower part is the homosphere up to about 90 kilometers. Homospheric means the gases are fairly well mixed, so composition stays almost uniform. Above that is the heterosphere, beyond 90 kilometers, where gases start stratifying by weight. Heavier gases stay lower, lighter ones dominate higher up. By temperature, remember the layer is defined by how temperature behaves with height. Troposphere is the weather layer and holds around 75% of the atmospheric mass. Temperature generally drops by about 6.5 degrees Celsius per kilometer. Then comes the stratosphere, where temperature rises, mainly because the ozone layer absorbs UV and heats this zone. Then the mesosphere, where temperature drops again and reaches the coldest values, around minus 100 degrees Celsius. Above it, the thermosphere, where temperature rises sharply. Here's a trap you need to be aware of. Students imagine the tropopause as a flat boundary. It is not. It rises to around 18 kilometers near the equator due to strong convection and comes down to around 8 kilometers near the poles. Now connect structure to function. These layers aren't just names. They protect you and enable communication. In the stratosphere, the ozone layer absorbs harmful UV radiation. That's why this zone becomes warmer upward. In the mesosphere, meteors burn up due to friction. So this becomes a protective shield again, but in a different way. In the thermosphere, the ionosphere matters. It's full of charged particles, and that's why phenomena like aurora borealis appear and why radio waves can reflect over long distances. If you remember only one pattern, retain the temperature zigzag. Down in troposphere, up in stratosphere, down in mesosphere, up in thermosphere. Now move from layers to temperature on Earth. Temperature is never controlled by one factor. It's a bundle. Latitude matters because sun rays are direct near lower latitudes and oblique near higher latitudes. Direct rays concentrate energy. Oblique rays spread it. Altitude matters because of the lapse rate idea. Higher altitude usually means lower temperature. Distance from the sea matters because land heats and cools faster than water. Coastal areas stay moderate. Interiors show extremes. Ocean currents rewrite local climate. Warm currents raise coastal temperatures. Cold currents cool them down. Vegetation influences heating because darker surfaces absorb more. Forest cover also affects humidity and local heat balance. And slope aspect matters. A south-facing slope receives more sunshine in the northern hemisphere, so it tends to be warmer. Most students list these. Toppers connect them. That's the difference between a 2-marker and a 10-marker. Now we enter the real engine: planetary winds and pressure belts, driven by unequal heating. Think in 3 circulation cells in each hemisphere: Hadley cell near the equator, Ferrel cell in mid-latitudes, and polar cell near the poles. This creates a pressure belt pattern: equatorial low, subtropical highs around 30 degrees, subpolar lows around 60 degrees, and polar highs near 90 degrees. From these belts, the wind belts fall into place. Trade winds blow towards the equatorial low. Westerlies dominate mid-latitudes, often remembered with roaring 40s. Polar easterlies flow outward from polar highs. Here's a trick you need to be aware of. Wind names come from origin, not destination. So westerlies blow from the west, not towards the west. Now add motion. These belts are not fixed. They shift seasonally because the sun's vertical rays shift between the tropics. On June 21st, summer solstice in the northern hemisphere, the whole belt system migrates northward. On December 21st, winter solstice in the northern hemisphere, it migrates southward. A clean way to retain it? The atmosphere breathes with the sun. Belts follow the heat. And that shift has real outcomes. Example given here is the Mediterranean pattern. Winter rain and summer dry happens because the wind/pressure zones shift so that westerlies and cyclonic activity dominate in winter, but subtropical highs dominate in summer. Now you can understand the monsoon like an adult, not like a slogan. In summer, strong heating creates low pressure over Tibet or India, and moisture is pulled in from the ocean. The ocean remains relatively higher pressure. Winds blow landward, bringing rain. In winter, the land cools fast, creating high pressure over land, so air flows outward towards the ocean, where pressure is relatively lower. That's why the winter monsoon is largely dry for most of India. Mechanism-wise, two lines must come together. Classical explanation: differential heating between land and sea. Modern explanation: northward shift of the ITCZ. ITCZ is the Intertropical Convergence Zone, a zone where trade winds converge and air rises, creating cloudiness and rainfall. Here's a trap you need to be aware of. In answers, if you write only differential heating, your explanation stays incomplete. High-quality answers explicitly add the ITCZ shift. Now zoom into local winds, because UPSC loves asking small concepts with clean diagrams. Sea breeze, day. Land heats faster. Air rises over land, so cool air moves onshore from the sea. Land breeze, night. Land cools faster, so cool air moves offshore from land to sea. In mountains, valley breeze, day. Warm air moves upslope. Air rises up the slope. Mountain breeze, night. Cool, dense air moves downslope, sinking downward. Then come the snow eaters, Chinook in the Rockies and Fen in the Alps. These are hot, dry winds that can melt snow quickly and can even help in ripening crops by warming the leeward side. Now rainfall. Don't learn rainfall types as three separate stories. Learn one idea. Rainfall equals uplift. The only difference is what caused the lifting. Convectional rainfall. Heated ground makes air rise fast. Common in equatorial zones, often gives thunderstorms. Orographic rainfall. Moist air is forced up a mountain on the windward side. Leeward side becomes a rain shadow. Cyclonic or frontal rainfall. Warm air is lifted over colder air along fronts, giving widespread, longer duration rain. If you write this in mains as uplift is the common requirement, your explanation looks organized immediately. Now the heavy hitter, tropical cyclones. Formation needs a recipe, and temperature is the entry ticket. sea surface above 27 degrees Celsius. Then you need large sea surface as fuel because warm water provides moisture and latent heat. Coriolis force for spin, a pre-existing low-pressure system to organize inflow. Now the structure. The eye is calm, low pressure with subsiding air. The eye wall is the violent ring, maximum wind velocity and heaviest rain. Outside are spiral bands, the outer cloud bands. Here's a trap you need to be aware of. No cyclones exactly at the equator because Coriolis force is zero, so there's no meaningful spin. Now compare tropical cyclones with temperate, extratropical cyclones because UPSC loves difference formats. Tropical cyclones, small, tight swirl, form over sea only, generally move east to west with trade winds, more violent and destructive, smaller area. Temperate cyclones, large, sprawling, wave-like systems, can form over land and sea, generally move west to east with westerlies, bring more gradual rain and are usually less violent, cover a larger area. And one key term here, occlusion. It's the stage when the cold front catches up with the warm front and the warm air gets lifted off the ground. That's when the system starts weakening. Now lock the global vocabulary. Because the phenomenon is same, names differ by ocean basins. In the Atlantic near the Americas, it's called a hurricane. In the Western Pacific near East Asia, it's a typhoon. In the Indian Ocean region, it's commonly called a cyclone. Near Australia, you'll hear willy willies. Then the opposite of cyclone, the anticyclone. This is a high-pressure center. Air sinks, skies are clear, and weather is usually calm. If cyclone is rising air and storms, anticyclone is sinking air and stability. Now tie the entire chapter into one line and one flow. Climate works like a chain reaction. Energy to pressure to wind to weather. Sun and latitude create temperature differences. Temperature differences produce pressure belts. Pressure belts generate winds like trade winds E to W and westerlies W to E. Then winds, uplift and fronts decide rain. Convectional, relief, frontal. And finally the big systems show up as storms. Cyclones, low pressure, and anticyclones, high pressure. Here's your homework. Write this chain in your own words in 4 lines. Then add one Indian example to each. One for monsoon, one for orographic rain, and one for tropical cyclones. If you can do that without looking, you're exam ready.